Electromagnetic induction. This is it's kind of the reverse of the motor principle, and it says that a moving magnetic field will induce an electric current. So we said the motor principle said that, well, not the motor principle, sorry, Oersted's principle said that if you had an electric current, you could create a magnetic field. This is just saying the same thing but in reverse. However, there's a difference, which is that you can only create an electric current if you have a moving magnetic field. If it's not moving, it won't. Just having, for example, just having a magnet sitting there near a conductor isn't going to do anything. And I have a little demonstration to show you, which I will. If I haven't already, you will see that soon, why that's true, or not why it's true, but just see that it's true. So most electricity generators use this principle. You have some force causes a to turn a turbine, and imagine this is the turbine in here. The turbine will have a magnet inside of it and a coil, and that moving magnetic field will create electricity in the coil. So in other words, inside of here it should look just like a motor. I've got a fixed magnet, I've got a coil, this thing spins, I generate electric current, and that's why it works. If it wasn't moving, then I could just have the windmill without spinning, and I could create electricity, which it just doesn't work that way. How does that? So the windmills, I think the windmills are the easiest example of that. But look at the hydroelectric power; it's the same thing. You've got you use the gravitational potential energy of the water, right? It comes down, it causes the turbine to spin. And inside that turbine is a fixed magnet in a coil, and that spinning of the turbine moves the magnetic field, or it moves the coil. Usually it's the coil that turns, actually, but as long as they're moving with respect to each other. And then same thing, you make electricity. Nuclear power is the same thing. What really happens in a nuclear power is you have the nuclear reaction where it's fission, and fission means that we're splitting uranium atoms. They split out, I think it's usually uranium anyways, not always, and they split, and when they split, there creates a huge amount of energy. Well, that energy just heats water, right? Heats water to create steam, and that steam, the pressure of the steam, causes the turbine to spin. When it spins, then you got a magnet, and you got your coil, and you have your electricity. So even though we say it's nuclear power, well, it's just what you're using to spin your turbine. Okay, they're all really done the same way. Now, electric power generation doesn't use Faraday's principle would be a battery. A battery doesn't do that. A battery is just a chemical reaction, or a solar panel, which is kind of the same. A battery and a solar panel are closed-term principle, but most of the big-time electricity generators happen this way. Oh, coal. Sorry, coal is the exact same idea. You burn the coil, which heats, burn the coal, which heats the steam, water, creates steam. The pressure of the steam spins a turbine. Inside the turbine, you got a magnet, you got a conductor, and they're all the same thing. Okay, and notice these transformers. We'll get to that later. So that's great. So that's all you do. That's how you create electricity. Now and this is hard to get, but Lenz's law tells us that there's a catch. Okay, and what it means is that because electricity will create a magnetic field, right? So let's use a windmill just because it's easy. You spin the turbine, you generate your electricity. Well, the electricity in that coil that's being created will create its own magnetic field, right? Because it does, that magnetic field is always generated in the direction such that it opposes your motion. And the thing is, this is the thing. If, for example, the magnetic field generated a current, and that current generated a magnetic field that didn't oppose the motion, but attracted it, like caused it to want to move more, then you would have perpetual energy, and that would be awesome. It never works that way, though. So Lenz's law we actually apply Lenz's law specifically because in something like the drop zone here, these are the way these are created is like the way the brakes on a machine like this is that it's like this is like a giant magnet. They actually, probably it's an electromagnet, but they make an electric, make the riders sitting on a magnet. And they allow a conductor to be down the pole here. So when you drop the magnet, that's going to create a magnetic and a current inside the conductor. Like it would be like be wrapping around. Probably on the inside, it's wrapping around. And then that dropping magnet will generate an electric current inside the tube here, right? And it's going to be wrapped around. It's going to create that in a direction that's going to oppose the motion of the magnet, slow the whole thing down. That's just an example. So let's look at look at it like this, okay? So let's say that what we want to do, the skill we need to get is to be able to predict the direction of electric current inside a coil. So these aren't the greatest pictures, but here I've got a magnet. This is a bar magnet, which isn't how a generator works, but this is just learn Lenz's law. So I got a bar magnet, and this is me pulling on that magnet. I'm forcing it away. This is the coil. So we want to know, well, which direction is the current going to flow through this coil? So it says make note of the direction of the motion of the magnet. So it's moving to the right. Again, I'm forcing it. I'm making that happen. Okay, it's not moving naturally. I'm forcing it. The polarity of the coil will oppose the motion of the magnet. So in other words, I'm going to know if this is a north end or this is the south, or sorry, this is north end or south end right here, because it's going to oppose what I'm doing. I call this the George Costanza rule, by the way, because most people look at this and say, oh, this must be south here, because this is south and it's moving away. But that's not. You have to go against your instinct. If you know George Costanza, he had a rule that always move against. If he did exactly the opposite of what he thought he should, then he was right. So I'm telling you now, this is going to be north. It's going to be north because I got to work to pull this away. Right? So the south wants to stay here. I got to work to pull it away, so this has got to be north. So yes, it is north. Okay, and here's why. You're going to again go against your instinct. Next, but I still don't know the direction of the current through the coil, but now I just use the left-hand rule for coils. So I get my thumb to point to the north there, fingers wrap around, and then I can figure out the direction of the current. Okay? So my little arrows show that, kind of go up the front, down the back, up the front, down the back, up the front, down the back. And that's the direction of the current, and now I know which way it's going through the ammeter. Just change the setup, but here we go on another one. So now I'm forcing this north into here. I'm forcing it. That arrow says I'm pushing it. I'm using all my might to push it. So because I'm pushing it, this must be north to oppose me, right? It's not coming on its own. I'm forcing it in. And then I use my left-hand rule for my coil. You should be practicing this right now. Get your thumb to point up, get your fingers to wrap around this coil, and that'll show you that that's the direction of the current through the coil. So here's just two examples. These are messy examples I drew. So this, I want to say which way is the current flowing in here. I know this is north and it's being pulled away, forced away. Okay, and in this one instead, can I figure out which direction the magnet's moving? So I want to know this part. I want to know, am I forcing this away or pushing it in? So I know the direction of the current, right? And then the third example, which end of the magnet is south. Okay, so now I know there's a north end and a south end. I know I'm forcing it in, and I know the direction of the current, but I don't know which end of this is north and which end is south. So the answer here is, because I'm forcing the north away and I'm forcing it away, this must be south. So therefore, now I use my left-hand rule for coils, and it shows that my fingers are pointing down around the front. Okay, that's the answer to that one. which way is the magnet moving in this one? Well, it's to the right, and let's see why. If this is south, then this must be north to oppose me pulling it away. No, I lied. This is north, I lied. That part I didn't know yet. This is north because I have the current flowing up. So I use my left-hand rule for a coil, and this is north. So if this is north and this is south, this must be away because I have to pull it away, right? It has to be work for me to pull it away. And then which end of the magnet is south? Well, the answer obviously is the left-hand side of the magnet, but the reason is if the current's flowing down this way, use my left-hand rule, which makes this north and this south, and I know I'm pushing it in, so I have to use work to push it in, so this must be south. Because if this was north, I wouldn't have to push on it. It would go on its own. Okay, so how does that work? How can we use that to look at a current generator? So hopefully by now I've shown you in class the generator we have, and it should look very similar to this. You've got a north end, a south end, that's the fixed part, just like the motor, and this looks exactly like a motor, right? And notice this is what we call an alternating current generator, and we'll talk about that in a minute. So here's what's happening inside this thing. First of all, there's no split ring, but these brushes are the same as on the motor, where they're not a permanent connection. This ring here is allowed to rotate. Okay, so this spinning has happened because it's being forced, right? It's being forced either by, if it's a hand crank generator, by your hand. If it's a windmill, it's being forced by the wind. Something's forcing it to turn. Okay, so it's being pulled. This is the fixed magnet again. Yeah, there's my armature, my coil, all that stuff. So what's happening here is I'm forcing this to move, right? So what you should remember from Lenz's law is I'm forcing it to move, so this has got to be the south end of the coil because I have to pull, I have to work to get it away from here. If this was north, then it would move on its own, right? So when I'm pulling it, this must be south, and because it must be south, the direction, using the left-hand rule for a coil, of the electron current is then dictated, right? So if this is south, this is north, use my left-hand rule, and that shows me the direction of the current. And then if you follow it through, you see where it's coming out here, right? If you follow that through, if this is south, my fingers are wrapping up and around that direction, so electrons come up, and just watch on here, this is my meter just showing me that that's the direction of the electron current. And notice I say alternating current. Specifically, it's an alternating current, so keep an eye on this as we move through the slides. Yeah, so we talked about this already, so this is just the same slide with my explanation. Then after this, as it gets to here, again, I'm forcing it. Well, again, once I get to here, to the horizontal, if I keep forcing, I won't have to force it anymore because now it wants to get away from here, right? So what changes? Well, because of Lenz's law, as soon as this happens without me doing anything, the polarity on my armature changes. Well, the direction of the current changes, causing the polarity to change, but this becomes north. So again, I'm pulling this away. As soon as I start pulling it away from that south, this becomes a north end because I'm working, because obviously it wants to be close by. So it was south up to here, and when this became a north end, bring your eyes up here, the direction of the current changed, and that is alternating current. It actually changes direction. Now the electrons are flowing out this side, up and around. Okay, so this is now changed the direction of the electron flow out of my generator, and that's the definition of alternating current. A direct current is what comes out of a battery. The electrons always flow in one direction, and that's what happens in this one. And the thing works exactly the same thing as an alternating current generator, except for it's got a split ring. So a direct current generator has a split ring, an alternating current generator does not. And this split ring allows the direction of the current to reverse every half turn. So if we follow the train of thought here, Okay, this is the exact same as it was before. Nothing's changed. Okay, like in the first step, the direction of the current is there. Oh, whoops. Oh, I don't have the rest. Okay, well what happens is the split ring means that when it gets to here and this south on south, it means that this brush will be by that point will be connected to the B side. And what that means is that even though the direction of the current on this piece has changed direction, what comes out is still the same. And that's a direct current generator. So I'm going to stop this video here because I have another, I want to show you the other video to go with it.